Hey everyone, and welcome. Today, we're diving into a concept you probably think you already know, resistance. But, in the world of alternating current, or AC, what we think of as simple resistance, well, it's really only half the story. There are these unseen forces at work, and once you get them, you'll see how pretty much all modern electronics work. So let me just ask you this straight up. You've got a resistor. It's stamped 10 ohms right on it. Does that mean its opposition is always 10 ohms no matter what? You might just be surprised to find out the answer is a big nope. And by the time we're done here, you're going to know exactly why. All right, so here's our game plan. We'll start with the simple story of resistance, the stuff we all know. Then we'll see how AC just messes everything up. We'll meet two new players called reactances, and then we'll put it all together to get the full picture with impedance. And finally, we'll draw it all out with the impedance triangle.
Visit youtube.com/avidsystem and don't forget to subscribe.
Okay, first things first, let's go back to basics. We got to start in the simple, predictable, and frankly, kind of boring world of direct current, or DC. See, in a DC circuit, the current is just flowing in one steady direction. It's like a nice, calm river. And in this world, resistance is simple. It's just a constant opposition. You can think of it like a narrow section in a water pipe. It just squeezes the flow, and that restriction never changes. And here's the key thing to remember. In the world of DC, resistance is it. It's the one and only thing getting in the way of the current. A simple one-on-one fight. But what happens when the current itself stops being so simple? And that brings us to AC. We're now switching from that calm, steady river of DC to the chaotic, back-and-forth sloshing of alternating current. This, right here, is the game changer. AC isn't a steady push. Nope. It's a constant cycle of push and pull, rising and falling, over and over again. And it's this constant state of change that awakens these other hidden forces in a circuit. So that leads us to the big question, right? If the current is always in flux, just constantly changing, how do other components, like inductors and capacitors, how do they react to this non-stop change? Because their reaction, that's where things get really, really interesting. And that reaction actually has a name. Well, two names to be precise. Let's meet these hidden forces that only ever show up in AC circuits, the reactances. So first up, we've got inductive reactance. An inductor, it stores energy in a magnetic field, and it absolutely hates any change in current. Why? Because to change the current, you have to fight its magnetic field, and that field pushes right back. It's like having a big, heavy water wheel in our pipe. It's got inertia, and it fights you every time you try to speed it up or slow it down. And then we have its counterpart, capacitive reactance. A capacitor stores energy in an electric field, and it fights against any change in voltage. This is more like having a flexible rubber diaphragm stretched across the pipe. As the pressure builds on one side, that diaphragm stretches and it pushes back. It has to charge up before it lets the current really flow. Now check this out. This is how these two reactances behave as the AC frequency changes. See the line for the inductor? As the frequency gets higher, its reactance just shoots up. The faster you try to change the current, the harder it fights back. But look at the capacitor. It does the exact opposite. A higher frequency actually means less reactance. They are perfect polar opposites. So we have our regular, boring resistance, plus these two new frequency-dependent reactances. How in the world do we get one single number for the total opposition? Well, that brings us to the main event, impedance. Impedance, which we represent with the letter Z, is the master term. It is the whole shebang. It's the total, all in opposition to current in an AC circuit. It accounts for everything, the simple resistance and the two reactances, all measured in ohms. But here's the catch, and it's a big one. You can't just take resistance and add it to the inductive reactance and the capacitive reactance. It is not that simple, because these forces, they aren't all pushing in the same direction. So here's how we actually figure it out. First, since the two reactances are perfect opposites, they're in a constant tug of war. So we find the winner by just subtracting one from the other. Then, this net reactance gets combined with the resistance. But they act at a right angle to each other, which means we have to think geometrically. Yeah, like the sides of a triangle. And that way of thinking leads us straight to this formula. And hey, does that look familiar? It should. It's just the Pythagorean theorem. The total impedance squared equals the resistance squared plus the net reactance squared. It's high school geometry, but for electronics. A formula is great and all, but a picture makes it all click. So let's actually visualize this relationship with something we call the impedance triangle. This simple shape is honestly the most intuitive way to understand how these three separate forces, resistance, reactance, and impedance, are all connected to each other inside an AC circuit. And there it is, the horizontal line on the bottom, the base of our triangle, that's our pure resistance, R. The vertical side, that's the net reactance, X, the outcome of that tug of war between the inductor and capacitor. And the hypotenuse, the long diagonal line connecting them, that is the total impedance, Z. You can literally see the Pythagorean theorem right there in that shape. This quote just sums it up perfectly. Impedance is the vector sum of resistance and reactance. That's just the fancy technical way of saying what the triangle shows us so clearly. We can't just add the numbers. We have to think about their direction. And the triangle does that for us. So let's do a quick recap. In a DC circuit, all you have is resistance. Simple. In an AC circuit, the total opposition is called impedance. And impedance is a combination of that simple resistance and this new thing, reactance. And the most important part, reactance changes with the signal's frequency, which means the total opposition of your circuit changes with frequency too. And that brings us to one last, really interesting thought. We saw that the two reactances are always fighting each other. So what do you think happens at that one very specific frequency where they are perfectly equal and they cancel each other out completely? The circuit's opposition would suddenly plummet, but that's a story for another time.
Thanks for watching.